All right, so chapter 15, section 1, we're going to be talking about functions of several variables. So in our mathematical career up to this point, we've usually dealt with functions of the form of one variable, where it would be something like f of x equals 3x squared plus 2x plus 1. So we have one input, and then we would have one output, f of x. Well, we want to now expand that definition. So recall, a function is a rule that pairs an input with an output to make an ordered pair. So, for example, let P of C be 8 times C, where C is the number of cups of pancake mix and P is the number of pancakes that can be made. Then the function value, P of 1 equals 8, would tell us that 1 cup of pancake mix can make 8 pancakes, or as an ordered pair, we would have 1, 8. In real life, functions almost always involve more than one input variable. So in that example, it was pretty simple. Our one input variable was 1 cup of pancake mix, gave us an output of 8 pancakes. So our only input was the number of cups of pancake mix. But in real life, pancakes have more than one ingredient, right? So there would be other things we would probably have to mix in. So there would be several variables that would be used. So let's take a look at this example. So it says, a company makes two types of laptops, the E271 model and the P314 model. The total monthly cost to manufacture X E271s and Y P314s is given by the cost function C of xy is equal to 400x plus 750y plus 1200. So we want to analyze this and answer the following questions. So what does each term in the formula represent? And what is C of 5100? And what does it represent? So similar to our previous function, if I had P of C, which equaled 8C, as we did above, we had P of 1, but if I did P of 3, that would tell me everywhere I saw a C, I replaced it with 3, right? Well, multivariate functions are going to behave exactly this same way. So let's analyze what each of these variables are and what they represent. So we were told that x represented the E271s, so that's going to be our x. And we were told that the y represented our P314s. So these are two different types of laptops. Well, if I look at this function, I notice a couple of things. So each time I do something, something is going to change. So let's go with our first one. Well, what if I put 0 in for x and 0 in for y? Well, if I do that, that's going to give me the following for my function. I would have 400. I replace the x with 0 plus 750 times 0, which I input for y, and then plus 1200. Well, we like 0 because 0 times anything is equal to 0, right? So that's 0, that's 0. So what does C of 0, 0 equal? 12,000. So first of all, well, what does this represent? Well, the 1200 is or 12,000 is the constant term from our function. So in terms of this business application, the 12,000 represents the base manufacturing cost or the fixed cost. So the constant term is the fixed cost. And that cost doesn't change. Whether you make 0 laptops or 1,000 laptops, it's going to cost the same, right? Or the fixed cost will be the same. The other things will change, but the base fixed cost will always be the same. So now, what do the coefficients of x and y represent? Well, let's take a look and see what happens. Well, what if I were to evaluate the cost function, instead of at x, I evaluate it at x plus 1. And y. So then that would tell me everywhere I see an x, this time I'm going to replace it with x plus 1. So then plus 750y plus 1200. So then if I were to distribute into my parentheses, I get 400x plus 400 plus 750y plus, I have a typo in the previous line, 12,000. So now I'm just going to rearrange a couple of terms. So if I take these guys, I have 400x plus 750y plus 12,000, and then I've got this extra plus 400. The reason I chose to do that is this part that's in red is really just the function c of xy that we started with. So now, if I write this down, that gives me then that I have c of xy plus 400. So if we go back to the very beginning, what was it that I did? I replaced x with x plus 1. So in essence, what does that represent in terms of this function? Well, what is the difference in cost of manufacturing x laptops versus x plus 1? So this represents right here the cost of manufacturing one more of the laptops represented by x, or the E721s. And that is called the marginal cost. So each E271 increases the cost by 400. This is called the marginal cost. So we may notice something in this problem or in this function when we started. We replaced x with x plus 1 and we got 400. But if we look back at the original function, what was the coefficient on the x? 400. And in this case, it's not coincidence because this is a linear function in both x and y. So this is a linear function. So the cost function in this example is a linear function of two variables. So what that means in this case is, since it's linear, that means each of the terms is linear. So if we go back to the original function, if I were to just cover up and ignore the y term, I would be left with 400x plus 12,000. Well, that would be a linear function in x. And if I covered up the x term, I would be left with 750y plus 12,000. That would be a linear function in y. When each of the components are linear, any addition or subtraction of them will also produce a linear function. We'll notice that the slopes of each of those give you the marginal cost for each. So the marginal cost for the E271s was 400. Well, that was the coefficient on the x, or the slope on the x term. The marginal cost for the P314s would then be 750, because it is the coefficient on the y term. So this thing that we did for marginal cost, where we did the shortcut, not the long way, only works if the function is linear. We'll do a nonlinear example in a second to see when it's a little bit more complicated. So keep that in mind as we go forward. All right, so the next thing we want to talk about is going to involve some of these graphs here, and that is the domain of a multivariate function, or some kind of restriction. So if we were to analyze this function, our function that we have here, not in red though. So c of xy equals 450x plus 750y plus 12,000. So let's talk about the domain. So with a lot of these application type problems, can I manufacture -5 laptops? No, that's not possible, right? You can't manufacture a negative number of things. In fact, the smallest amount of laptops I could possibly make would be 0, right? I could make 0 P314s and I could make 0 E271s, but I can't make a negative number of laptops. That doesn't make any sense. So for the domain, since we can't make a negative number of laptops, both x and y must be greater than or equal to 0, right? Because you can't make negative laptops. That just doesn't make sense, right? That's like me trying to say I want to be -5 feet tall. No matter how hard I try or know how much I aspire, that is not a possibility. So we get the first thing. The other thing that will happen oftentimes in business applications is that we will be limited on how many of something we can manufacture, right? Because in theory, you can make as many laptops as you want, but in real life, there's not an infinite number of resources, right? They cannot make an infinite number of laptops. They would eventually run out of stuff. And in reality, it's usually a lot smaller than that. So we could have some other restrictions as well. So we can get some interesting things that happen with our domain. So one example would be x would have to be less than, say, 75, and y would have to be less than 100. And that would tell us that we can make at most 75, and I forget which one were x again, E271s, and we could make at most 100 P314s. So if we were to look at something like that in terms of our domain, if we take a look at our graph, we could have something like this. So the axes are a little light, so I'm going to do this. Here's my x, here's my y. And I'm going to scale this in 25, so 50, 75, 100, 25, 50, 75, 100. So if I know that x has to be less than 75, that would be here. I'm going to mark that part in yellow, so that would be all of this. And I know that y has to be less than 100, so that's going to be here. So that would be everything below that. The domain is what is in green here, is the intersection of those two sets. So we knew it had to be bigger than 0. So this part right here, this rectangle, so the domain is the rectangle with the following. So 0, 0 to 75, 0 to 75, 100 to back to 0, 100. There we go. And that would give us the rectangle that we're seeing there in green, right? So our domains for multivariate functions can be a little more complicated. We could also have something that would be a bit more interesting. So the second example of a domain for something like this, well, what if only 100 total laptops can be made? Well, that would tell us then that x plus y would have to be less than or equal to 100, because x is the number of E271s and y is the number of P314s. So if we can only make 100, then x plus y has to be less than 100. So if we look at our graph again this time, we could do this one of two ways. So we have x plus y is less than or equal to 100. And minus x, I could minus x. And that gives me y is equal to negative x plus 100. So once again, if I scale this graph in 25s, so I'll just do 50 and 100, and then 50 and 100. If I were to graph the line y equals negative x plus 100, it would have y-intercept 100 and slope negative 1, so it would go here. My domain would then be this triangle that we're seeing right here, because as I increase the number of one laptop, I have to decrease the number of the other at this boundary point that we're seeing here. So the domains can be a little more complicated based on how we have some of these things. All right. So now I kicked the notation around for a second, and I said linear function, but we're going to make it very, very formal now. So we've got our graphs, our domain. So let's talk about the formal definition of a linear function. A function of n variables is linear if f looks like this. So f of x sub 1, f of x sub 2, all the way out to f of x sub n is equal to a1 x1 plus a2 x2 plus all the way out to an xn. So what this notation means with the subscript is instead of writing f of x, y, z because we run into the end of the alphabet, if we need more than 3 variables, instead we'll call everything x and we will put a subscript on it to indicate that it is a different variable. So just to be very clear, if I had the function f of xy equals 2xy, this would be the same as the function f of x1 x2 equals 2 x1 x2. It's just a different way to write things, but since we usually start with our variables at x, we run into the end of the alphabet after 3 letters. So if we have more than 3 variables in something, we will start using subscripts to indicate different variables. If it really bothers you, you can change them to different letters. It means the same thing, but that is the standardized notation with that. So back to our definition of linear. Linear means that there are no products in any of the variables. So we would note that this example is not linear because it has x1 times x2. In the above example, what we have the only variables are the x1, x2, x3, all the way out to xn, and they are never multiplied or divided together. So basically it's things of the form like this, 3x, where we have a slope and exactly 1 variable. So they're exactly like each part is a linear function like we knew when we had only 1 variable. And then you can add as many of those up as you need to continue to have a linear function. So for example number 2, we have a linear function. This is linear in both x and y. So let's go ahead and evaluate a couple of things. So if I were asked then, I want each of you guys to take example number 2, and I want you to find f of 10, 20. Evaluate that and see what you get. So what is f of 10, 20? All right, so to calculate f of 10, 20, we would substitute in 10 for x and 20 for y. So that would give us 60 minus 60, which gives us the number 0. So that is our output corresponding to the input 10, 20. All right. So the next thing we need to talk about is another definition and then an example that goes along with it. So we take a look at our next definition, and it is called a second order interaction function. So a second order interaction function is a function of more than one variable that has a product, that has a term that is a product of exactly 2 variables. So just to make clear, if we take a look at example 3, we'll notice it's pretty much the same function you guys just used, except for now we've got this extra term. This term right here is a second order interaction because it is a product of exactly the 2 variables x and y. So this is the product of exactly 2 variables. So this is an example of a second order interaction function. All right, so we've got this function, and something that will come up a lot is we're going to want to make a table of values. And we used to do that in our other math classes by using a table function on a graphing calculator. Well, this is going to be a little bit different because now our function has more than one variable. So for us to do this, one of the tools that we're going to want to use is Excel. So I'm going to pop open Excel and let's talk about how we're going to do this. So when we're going to do this, there's a few different ways that we can do this, but let's make a numerical table for all the values of this function between -3 and 3 at whole numbers. So the easiest way to do this is we are going to place where we want to start here in A1. So we're just going to type in -3. So then moving over to the next cell, in cell B1, I'm going to press my equal key, and then I want to reference the cell that came before it. So I will type in its address, and if I look at the grid here, I have an A, and then I have a 1, so I will say A1, and then I'm going to go +1. And it says -2, and you're like, well, why didn't you just type -2? Well, because now I can just copy and paste that formula over by holding down Shift, and then, so I'm here, hold down Shift, click all the way over to H, right-click and choose Paste, and now it's going to fill in those values. I can do the same thing here to fill out the rest of the values that I'm going to want for my table. Oh, I need to change this. So now I'm done there. So I go to, now I go to A2, and I need to make the reference to A1 again. So I press my equal sign, and I go A1, once again, +1. Then I copy that cell, and I need to copy it down. Until I'm far enough, and on both of those I went farther than I wanted, so I'll just delete these two. -3, and then at -4. Okay, so then this is going to allow us to do some calculations. So let's take a look at the rule that we're using. So we have 6x minus 3y plus 4xy. So I can type that in by using, I'm going to make my horizontal row is going to be my x's, and my columns y. If I want the table to go from -3 to 3, I started at the wrong place. So let's change it to 4, and then I need to copy one more. You always need to start one less than where you're at. So I'd done that. I mean, it would have been fine. It just wouldn't have given me the values I was looking for. You paste you down a couple more. Okay, perfect. So now I do have my values all the way out to 3. So I'm going to make my horizontal row represent my x's and my vertical column represent my y's. So I'm going to have equals, and I'm going to go 6 times, and then I want to reference my input, which is -3, but it's in the space B1. Plus, oops, I hit the wrong button, plus my next term is negative 3y. So instead of plus, I change it to a minus. So 3 times, and now I need to reference my a column. So we have times a times 2. Sorry, a2. And then we're going to have one more term, which is both of them together, the 4xy. So plus 4 times, we're going to have b1 again, times a2. And that fills out this very first column, which is nice, but we're going to have to make some modifications to Excel, because Excel does something very interesting that we exploited in the previous one. So let's explore what's happening in these cells. So when I look in A1, I see negative 4. When I look at B1, I see it says A1 plus 1. So it's saying look at this cell and add 1 to it, and it reports negative 3. When I look at the next one over, it says, okay, B1 plus 1. It says look left 1 and add 1 and get here. I copy and pasted that whole line over. When I did that every time, notice what happened to the first letter. It changed each time. So Excel, when you copy and paste cell references, it assumes that that copy and paste is going to keep referencing a new cell in a different location. So it assumed, because the first thing I asked it to do here was to look at the cell to its left. So all of the ones after I copied always looked to the cell to the left. So that's why we get C1, and then here it's going to be D1 and so forth. If we look here in the same column, same thing, A1 plus 1. As I go down, A2 plus 1, A3 plus 1, and so forth. So now that's going to cause some issues. So if I go ahead and try to copy this over to the next cell, it gives me negative 309, but let's see what cell addresses it actually put in there. So it said it used C1, it used B2, and B2 again. So the C1 is correct for my location, but what thing did I actually want it to use? I didn't want it to use B2. What was the input that I wanted it to use? I wanted it to use the input right there at negative 3, right? So there's a way that we can ask Excel nicely to do that. If you don't want one of the indices to change, you need to put a $sign in front of it. So I want all of my references in this line, they can change the number part for B, or they can change the number part, but they can't change the B. So what I'm going to want they can change the number part for A, but all of my inputs need to stay in the A column. So what I'm going to need to do then is when I input this, I'm going to put a $sign in front of the A2. And notice it didn't change the value in that cell, but if I copy and paste this over to the next cell now, I get a different value. And notice when I look here, it is still referencing A2 in those places. So it's still using the inputs from that very first column. So the $sign tells us to freeze that and not do the incrementing like what we saw here where it changed them as we moved right to left. Similarly, if we tried to copy this cell down, we're going to run into a similar issue. So let's paste and see what happens. So when I look at this column right here where I got negative 48, my B2, it's now referencing the thing above it. So what didn't I want to change? In this one, I want the numerical part of the columns here to stay the same, and the A3 was where it was going to be. So in this ones I did the A, and this one I do need the b's not to be changing. So let's go back up and edit our previous formula again. So this time we're going to put the $ in front of the 1. And what that's going to do is it's going to force that value to always stay in that top row, because the top row was column 1. So now we get this, and we'll notice it worked the way it was supposed to. We're like, okay, that's pretty cool. So let's finish pasting this in. So we copy and paste all the way down. And then we can actually go copy this whole thing. And then we, oops, I needed the whole thing. So go there, all the way down to here, copy. And then let's paste all the way out to here, and you can paste that whole rectangle now. Oh boy, what have I done? So let me do that again. So we go copy, and then we can just paste everything here and paste into that entire rectangle, and that gives us all of our function values for that function. So now if I wanted to say no, like if I looked right here, what does it tell me? That if I put in 0, 0, what's my output going to be? Well, I put in 0, I get 0. If I come down here, if I input 2 and 3, I get the following output, right? So we can do some pretty cool things with some stuff like this. Another thing that we can do with Excel is now if you take those and select that entire block of cells that we just made, I want you to go up to Insert, and we're going to choose that we want to make a chart. So we're going to go here. We're going to need more charts, not scatter. Where's our surface chart? There we go. So here we go to surface, and let's go ahead and create a surface. And Excel will actually create a nice three-dimensional graph of what that function looks like for you based on that data that we just created. So we'll see some applications of this shortly. So remember, a couple of things I do want to mention. So one last thing I do want to mention while we're looking at this, we'll notice now that as we change our variable, like if I were to go across this column here, so we'll notice that the first time I change in the column in this very first row, all of the changes are by negative or by 6, right? So we have something that goes like this. We're subtracting 6 all the time as we go down. But when we go to a different column, it changes. And that is what happens when we have that interaction term is what's causing this to happen. And it shows us that increasing something by 1 no longer gives you the same value or the marginal cost that was just the coefficient. So I mentioned earlier that the marginal cost was the coefficient if the function is linear. Another way to say that is if you don't have any interaction terms, or if it's not an interaction function, that will be true. When there are interaction functions, things are going to be a little bit different when we do that. So just note, let's see what the marginal change is in this example. So if I evaluate f of x plus 1 y, I'm going to replace x with x plus 1. I get 6 times x plus 1 minus 3y plus 4 times x plus 1 times y. So we distribute into our parentheses, and that gives us 6x plus 6 minus 3y. And I'm going to distribute this 4y into the parentheses together. And that's going to give me a 4xy plus 4y. And once again, we'll notice our original function is 6x minus 3y plus 4xy. So these three things together are f of xy. Let me write it out explicitly. So 6x minus 3y plus 4xy. And then we have a little bit more left over. We have a 6 plus 4y. So this is our original f of xy plus 6 plus 4y. So then this term is going to be like what we saw above when we figured out our marginal, where did we put that? All the way back up here, our marginal cost. So this is the marginal cost of x. In that case. So it says the cost to increase x by 1 unit is 6 plus 4 times the number of whatever y was. So unlike the previous one where we had only a constant term, the y value is now also affecting this. So when we have those interaction terms, things are going to behave just a little bit differently. All right. So we've got a couple minutes left here, so we're going to start talking about three-dimensional coordinate systems. So far we've been dealing with everything algebraically, and then we used Excel to draw a three-dimensional graph. So let's talk about, well, what does all that stuff in the three-dimensional coordinate system mean? So traditionally, when we're drawing a three-dimensional coordinate system, the x-axis is the one that's drawn to be coming out of the page, y is going to the right, and z would represent up. So we have our three-dimensional coordinate system, and we have our bits here. So instead of having quadrants, we have octants. The octant where everything is positive, when x is positive, y is positive, and z is positive, is called the first octant. None of the other ones have names, and nobody really ever uses them, so that's more just FYI. You're not going to be asked about it. But if anybody ever says the first octant, what they mean is the place where x, y, and z is positive. But our book sparingly uses that terminology, and nobody else really does either. So let's talk about graphing some things in the plane, or in this coordinate plane. So if I had the point 3, 0, 0, our ordered triple would be an x, a y, and a z. So it would say I would go 3 units in the x direction, no units in the y direction, and no units in the z direction. So I'd go 1, 2, 3, no right or left, and no up and down. So that would be my point 3, 0, 0. All right, let's try another one. What if I had the point 1, 2, and 6? Well, that would tell me I would go 1 unit out this direction, and then I would have to go 2 units in the y direction, so out here, and then I'm going to have to go up 6 units to my point here. So then I would have the point 1, 2, 6 would be floating up here in the plane. So first thing, I am not going to expect any by hand graphs to be extremely accurate. These things are super hard to draw by hand. That's why we have Excel. We're going to have other technology to do that. I do want you to understand the basics of how the geometry works. And as you can see, my lines are not all perfect, and since we're doing essentially a projection of a 3D object onto a 2D canvas, things get distorted, right? And they're not easy to draw. So by hand, do your best. If we really need to draw some things, we'll draw them in terms of using some technology as we go. All right, so let's take a look at our next one. So this one is for you guys. I want you to plot these points on the Cartesian coordinate systems. All right, so let's go ahead and try to graph this first one. So we're going to go 1 in the x direction, 4 in the y direction, and then we have to go up 5. So we're going to go up to point about right here. So that's going to be 1, 4, and 5. And if we try 4, 1, and 0, we're going to go 4 in the x, 1 in the y, and then 0 in the z direction. So it's going to be a point right there in the xy plane.